So what we're going to start with today is talking about the number systems or the sets of numbers that are exist in the world. Some of them are going to make sense to you, some of them you've never heard of before. But we need to be able to know about these number sets or number systems to be able to answer some of the questions today. The first type of number that we're going to deal with today is called the counting numbers or the natural numbers, okay? It is represented by this big fancy N. You know that big fancy R for all real numbers? Yeah, all of the sets of numbers, most of them have a fancy symbol. The fancy N is the natural numbers. These are the numbers you learned about when you were like 5, maybe younger. These are your counting numbers. 1, 2, 3, 4, 5, 6, 7. All of those are numbers that you would count with. They're called natural numbers. The second number set is called whole numbers with a fancy W for whole. Kind of makes sense. And all that the whole numbers are all of the natural numbers, but also include 0. So whole numbers are 0, 1, 2, 3, and on and on and on if we kept counting. Those are called whole numbers. Okay, so we have natural numbers, we have whole numbers. Making the set of numbers we're including a little bit bigger. The next set of numbers is called the integers. Integers does not have a symbol with an I on it. It has a symbol that's a fancy Z. Feels weird, but that's how you talk about integers. Integers are our favorite kinds of numbers because including all of these numbers, it's like the negative and the positive versions, including 0, of different numbers. So we're just adding more and more numbers into these sets. We started with natural. We added 0. That's now whole. We add their negative versions. Those are called integers. But no fractions just yet. Just all of the nice pretty numbers, both positive and negative, are called integers. If we go a step further and start adding decimals and fractions, those are called rational numbers. Rational is represented by a fancy Q, my personal favorite, obviously. But rational numbers are like adding in fractions. So let's say we had all of these numbers and we have -2, -1.5, -1, -0.3, 0. Any decimal that you can think of, those are going to be our rational numbers. Can be expressed as a ratio of numbers as a fraction. Okay. The next number system that we have is kind of like the opposite of what we just used. So rational numbers are all of the fractional numbers and all of the repeating decimals that could actually be fractions or terminating decimals like 0.1, 0.5. If you have a decimal that is not repeating and doesn't have an ending number, it's called an irrational number. It's like not rational, irrational. Some examples of that, and they're not particularly in a number line. Square root of 3 is a decimal that doesn't repeat. Square root of 27 is some number that doesn't ever repeat itself. These are called irrational numbers. Another example that's really common, square root of 2. Now, square root of 4 is the number 2, so not every square root is an irrational number. There's just some that don't reduce down or anything. Those are called irrational numbers. But if we combine all of the number sets that we studied before, so that were written on this paper before, we get to these real numbers. And look, there's the symbol we know about, the fun and funky R. We've been using the real number system in classes in algebra for a long time. This is talking about numbers from -infinity to infinity, including the rational, the irrational, the whole, the natural, I'm missing one, the integers. All of those are real numbers. So we just need to know what kind of number system we're using for some of these questions today. Now this is a lot of different symbols and a lot of different things. The main thing is if your notes or your problem asks for a specific type of number, just refer to the type of number it is here on your notes. That's kind of where we're getting at. But if you look on the back, we have this little diagram up here that kind of shows how we build up the real number system starting from the middle. So if you look at the very inside circle, that very inside circle is called the natural numbers. That's the smallest set of numbers that we have because it's just all of the counting numbers. If you add to that set the number 0, you've got the whole numbers. So our set has gotten bigger. If you add the negative versions of those numbers, you've created the set called the integers. So we're making, again, bigger sets of numbers. If you add in fractions, you've got the rational numbers. So all of those things are like contained in it's like a big Venn diagram-ish, right? All of these little circles are contained in the bigger one. We take a pause to the side to talk about the irrational numbers because they're not rational, so they can't be in the same circle as rational. But all of those numbers, rational and irrational, are a part of the real number system. So you've got a big old circle on the outside encompassing all of it called the real numbers. So again, this is just to help you pick and choose what kind of numbers you use on some examples that we will do today or that are on your homework. If it tells you about the whole numbers, use the whole number circle. If it says integers, use the integer circle. If it says real numbers, you can use literally all of them. Okay? But the goal really of today's lesson is to understand the difference between what's called interval notation and inequality notation. We've actually used inequality notation for like all of Algebra 1. This is the inequalities when we would write domain and range that we did in this class too. Left, a symbol, x, a symbol, and right. And then bottom, a symbol, y, a symbol, and a top number. Do we remember doing this? We did this one of the days in class here. When we were out in the hallway, we did the left, right, bottom, top for all of those functions on a graph. So we've done this before. We're just basically going to be looking at domains now, so just x-axes. You don't have to use a y right now. But let's look at these two number lines. I know it's hard to see because it didn't print very good, but let's write down the correct notation to represent this domain of numbers on this number line. Right here, what number is this little dot at, this open circle? -4. I know it's hard to tell, but that's -4. So we're going to say our left number is -4. It's an open circle, so the symbol that I put next, should it have the line underneath it? No. Great. I'm going to put an X in between them, and then I'm going to look on the right side. The next open circle is at what number? 7. And that's, again, an open circle, so it doesn't have the line underneath it. We've done this before. This is what we've been doing. Nothing has changed. Let's look at the second example. In the second example, when I look on the left side, I see an arrow. What is that arrow going to go off towards? Specifically, which infinity, positive or negative? Negative infinity, yeah, because that's on the left side. That's the negative side, so it's negative infinity. And then I have a closed-in circle on what number? -1. So if I were writing this the way I had been, I would say negative infinity less than x less than or equal to -1. Why did I put this line underneath here? Because it's closed in. Fabulous. Okay, but the problem is we're not allowed to leave infinities in our final answer for inequality notation. So what did I do when we did this? What did I do when we had an infinity? I marked out the infinity, yeah, and I flipped it if I needed to. Do I need to flip this, or does the x already come first? The x already comes first, so we actually don't have to flip anything. You only do the flipping if you actually need to flip it. So again, this is just a good little review. These are the ways we've been writing domains and ranges before we came to this class. But what I'm going to show you is a new notation called interval notation that I personally like better. I think it's easier, even though it's a technically more complicated or more advanced version of talking about domain and range. I personally think it's 1,000% easier. With interval notation, you are no longer using the pattern left symbol x symbol right. In interval notation, you're just going to tell me the numbers that you're using left and right and give them either a parentheses or a bracket to make an interval. Do you see how the words interval, comma, notation have a parentheses or a bracket? Do you see the difference? Curved, square? You're just going to be using those two symbols instead of the less than or equal to and the letter. All of that jazz is gone. It's just going to be a parentheses or a bracket. So specifically, the parentheses is used when the point is not included, which means the symbols that I would have used for less than or greater than, the open dot on a number line, the less than greater than, or the infinities, all get a parentheses. The brackets, or the square version, squarish looking version, is for when a point is included, meaning that or equal to part, or a closed dot on my graph. Now, to put all of this together before I really confuse you about all these symbols, we're going to draw two faces on our notes. I know there's not really room right here, but find some space maybe by the Venn diagram at the top to draw these two faces with me. It's just a way to help remember all of the things we just talked about. Here's the first face. For less than, greater than, and an open circle, you get a regular smiley face that's curvy. That's the parentheses. Additionally, this guy's wearing glasses, but those glasses are actually infinity sign. So if you are using an infinity or have no line underneath your symbols or an open dot, you get the parentheses. On the other hand, if you have the lines underneath your symbols or a closed dot on your number line, it's going to be a square mouth or a bracket. So these faces will help you pick the different symbols you're going to use in interval notation. This means nothing to you yet till we see some examples. I 1000% understand that. So let's look at these examples. Oh no, it didn't get stuck. Okay, number one I want you to notice is that these number lines are the exact same as the blue example. Do you see that? I didn't change the numbers at all because I want you to see how it compares to both notations. So if I was writing interval notation for this number line, what's the first number that it shows up with? What was that number? -4, and that's an open circle, so I'm going to put a parentheses around that number, just once. Then I go look at the other side. What number is this endpoint at? 7, and it's also open, so I just give it a parentheses. I'm done. There's no X, there's no other symbols, there's no nothing. You tell me left and right, and then you give it a bracket or parentheses. That's it. If we look at the second example, we attack it the same way. What's happening on the left side? Negative infinity, fabulous. What's happening on the right side? -1. Check this out. We get to leave negative infinity in my final answer. It just gets a parentheses. And then when we get to that -1, I switch to a bracket because -1 is included. That's it. I'm done. There's no cleanup. You can leave infinities in your final answer. I prefer interval notation. I think it's easier to write, in my opinion. It's technically a more advanced version. I think it's easier. But if you look, this is how you compare the two. Do you see how in the red we had the less than symbol because we had a less than symbol? And we had, again, the less than symbol because we had a less than symbol. Because we would have used the less than here, we have the less than symbol. And because we put the line underneath this symbol for or equal to, we switch to the bracket. That's it. Okay, let's do some example problems of this. I know I didn't fill in the bottom of this page. We'll come back to that in a second. Let's do some example problems of just switching inequality notation to interval notation. Okay, so how we're going to do this to help you out, it's always very helpful to draw a number line. So I've got number lines for you there to help you switch them, okay? On this first number line, we would put the numbers -2 and 3. Yes, I know it's not perfectly even spaced out at -2 and 3. I don't care. We just need the numbers on a number line least to greatest. On the number -2, would I have an open or a closed circle? Closed. Why closed? Because the line's underneath it, yeah. That means that this is a closed symbol. On the number 3, would it be opened or closed? Closed as well. Very good, because that's a closed symbol. My domain is just the numbers in between these two things. So from -2 to 3. I color in my number line. Okay. Well, we've got a closed circle on -2, and we've got a closed circle on 3. So to change that to interval notation, it's a closed circle at -2 and a closed circle at 3. You just switch them to brackets. The bracket is for closed, yes. The parentheses is for open. Okay? Let's try that second example. What are the two numbers I'm putting on my number line? -5 and -1. Again, they don't have to be perfectly spaced out because you can put the numbers wherever you want as long as they are least to greatest. Open or closed circle on -5? Open. Open or closed circle on -1? Close. Okay, that's fine. They can be different. I want this range of numbers in between them, the interval of numbers between them, to be in how I answer this question. So we started at -5, but it was open. We ended at -1 and it was closed. So I put a parentheses on -5 and a bracket on -1. Is it starting to click a little bit? Open circle parentheses, closed circle bracket. Cool. We will do one more example together, and then I'm going to have you try some. On example 3, it's different. There's only one number. No big deal. Put that one number on your number line. Would it get an open or a closed circle? Open. Okay, great. I've got this open circle. Again, it's open because there's no line underneath that symbol. Now I need to know which direction to color because there's no other number for me to put down there. This symbol right here is called greater than. Where are numbers bigger than? Are they bigger on the right or bigger on the left? On the right. So I'm going to color in on the right, and since I never hit another number, I'm going to go all the way to that arrow. And what number does that arrow represent? Infinity. Look, now I have two numbers on my number line. This is going to go from -1 to infinity. And the infinity can stay in my final answer. Infinities, because the guy with the glasses has the smile, not the square smile, is a parentheses. So any of the infinities is parentheses. If you're going to be confused on which way to graph, what I want you to notice on the symbols that look like this, if it was an arrow, it would tell you to color in that way. That's the greater than direction. And if your symbol happened to be this, and it was changed into an arrow, it would be telling you to color that way if you need help coloring. So again, the greater than symbol is like an arrow pointing to the right. That's the direction you color. If it's a less than symbol, it's pointing to the left, so you color it to the left. I want you to try the next 3 examples, example 4, 5, and 6, on your own. If you need help, raise your hand or quickly ask a question to the person nearby to you. Okay, let's see how we did. I'm seeing some really good stuff around the room, so let's just get a good check here. We would have on example 4, put a little closed circle on the number 5, and because it says less than, we would have colored to the left. And the left direction is our negative infinity direction. So my interval would be from -infinity to 5. The infinities are always parentheses. And the two faces you drew, those are the glasses you gave to that one, and that's the regular smiley face instead of the square smiley face. Okay, on example 5, we had 2 numbers on our number line, 16 and 27. They're both open circles. And since we have 2 numbers, we want all of the numbers in between them. So simply we're saying from 16 to 27, but they're both open, so they both get parentheses. On the 6th example, the number is -3 with an open circle. And since I want numbers that are less than -3, I would color in my number line this direction. Is that positive or negative infinity? Negative infinity. So the smaller number goes first. Negative infinity is real small. So that one goes first. That's the left number. And then we have the right number. But they're both technically open because they're both on the open face guy. So they both have parentheses. A lot of us are getting these mixed up and doing them backwards. Remember, negative infinity is very small. Positive infinity is very big. So negative infinity should always go on this one and positive infinity on the right. Yes? Okay. thank you for trying those examples. There's technically one more version, one more notation we're going to learn today, but it's not anything technically new. This very last notation that we didn't talk about down here is called set notation. In Algebra 1, you used sets to talk about just individual numbers, like coordinate pairs. You'd say all of the domains from a coordinate pair, you'd just like squiggly line it, and you'd list out all the domains. So something like this. You'd put the squiggly lines and put a bunch of numbers in it. Great. For what's called set builder notation, all you have to do, which is what we're working on, is take the original inequality that you would have answered for the problem and make it fancy by putting squiggly lines around the outside of it. And at the very beginning, you put an X and a big old line back down. All that says is it's all the set of X numbers such that. That big old line is the word such that. And then the regular answer. And let me prove to you how easy this is. Again, do you notice that these number lines are exactly the same? Like I didn't change the number lines at all from the blue example to now what's going to be the green example. And since set notation uses inequality notation, I'm just going to copy down my answers real fast. -4 less than x less than 7. I would have answered that part exactly the same. But I'm going to make it fancy. And the way that I make it fancy is I open a squiggly brace, put an X, put a bar, close it with a squiggly brace. That's it.
That's not a 1?
It's like a bar. Yeah, it's not a 1. Yeah. It's a big old bar. On your computer keypad, it's above the enter button, but you have to press shift. It's above the backslash. So again, it's just like answering the inequality notation, so which we did already. X less than or equal to -1. But for set builder notation, you just make it fancy. At the beginning, we add a squiggly line, an X, a bar, and at the end, we put a squiggly line. This part hasn't changed. This inside stuff is just how I'd answered it if it was an inequality. No different from what we've done all of Algebra 1 and so far at the beginning of this class. You just pop the extra fancy stuff on the outside. So if we do a few examples of that on the other page, we have 3 examples left. To make set builder notation for the whole numbers from 50 to 54. 1 second, we need to remember what whole numbers are. Flip your paper over. What are whole numbers? The counting numbers and 0. So can I use fractions? No. When I cannot use fractions, all we're going to do is list out all of the numbers. So let's list out all of the numbers from 50 to 54, including 50 and 54. So that's 50, 51, 52, 53, and 54. If I can't use fractions, I just pop all the numbers in there and call it a day, including 50 and 54. Fabulous. So that's, again, we use the whole numbers. That's my counting numbers and 0, so no fractions. And we just did from 50 to 54. In the second example, it asks for the real numbers. In real numbers, can I use fractions? Yes, real numbers is like all of the numbers. So I can use fractions, which means I now have to do an inequality. This says between 0 and 4. Does it say including 0 and 4? So my inequality, if I can't include 0 and 4, would just look like this. No lines underneath it because it's not equal to 0 and not equal to 4. That's the inequality. But to make it a set builder, all you do is pop the fancy stuff on the outside. Squiggly bracket, X, bar, squiggly bracket. The inequality part has not changed. Between 0 and 4, not including 0 and 4, that's how we write it, and then you just make it fancy. Last example, it says the real numbers greater than 5. So again, for real numbers, can I use fractions? Yes, so I have to do an inequality. But greater than 5, real easy. What's the symbol for greater than? Does it look like your left hand or your right hand? Your right hand. So x is greater than 5 is going to be my inequality. Simply just like it says, greater than 5. And we just make it fancy. Bracket, or sorry, squiggly bracket or brace is sometimes what they're called. X bar at the front and close it up with a squiggly one at the end.